All right, let's talk about one of the most elegant, most powerful ideas in all of physics. I'm talking about Hamiltonian mechanics. Now I know, it sounds super complex, but what if I told you it all boils down to one simple, absolutely brilliant idea? And that idea is just changing your point of view. Ready? Let's dive in. Okay, so take a look at this. You might see a bunch of symbols, right? But this is so much more than just an equation. Think of it like a passport or a secret map. It's our guide for traveling from one way of looking at the universe to a completely different and frankly much more powerful one. And you know what? Today, we're going to crack that code together. So to really get this, to decode this secret formula, we've got to start at the beginning. We need to step into a world described by a concept called the Lagrangian. Yep, our journey starts right here, in the world of L. We're talking about the Lagrangian framework. So what is the Lagrangian anyway? Well, you can think of it as a really clever recipe. It's a way to package up all the essential information about how something is moving. And usually it's pretty simple. You take the kinetic energy, that's the energy of motion, and you subtract the potential energy, which is all that stored up energy an object has just because of where it is. Now, if you look at how we write this out, you'll see that the Lagrangian, this L, is what we call a function of three things: Q, Q dot, and T. But what on earth do those letters actually mean? Let's break it down. Okay, it's actually pretty straightforward. Q is just a stand-in for position. It answers the simple question, where is it? Then you've got Q dot. Now, whenever you see a dot over a letter in physics, it just means the rate of change of that thing. So the rate of change of position, that's just velocity. It answers, how fast is it moving? And that's the key takeaway here. The entire world of the Lagrangian is built on just these two ideas, position and velocity. But here's the thing. Describing the world in terms of just position and velocity, well, it isn't always the best way to do it. What if there was a better, maybe a deeper way to look at the same problem? Well, this is where our story takes a really crucial turn. We are about to cross a kind of bridge, a bridge into a whole new way of thinking. Now, this bridge, it's got a pretty fancy name, the Legendre transform. But don't let the name scare you off. It's actually a really cool idea. Think of it like this. Imagine you're a business owner and you have a graph that shows your profit over time. Simple enough, right? The Legendre transform is like a magic tool that takes that exact same data and replots it. But this time, instead of showing profit versus time, it shows you profit versus how fast your profit is changing. See, it's the same information, just repackaged. It's designed to reveal new and often much more useful relationships hiding in the data. So here's the bottom line. The whole point of this transformation is to switch what we're focused on. We are literally going to stop caring so much about how fast something is moving, its velocity, and instead, we're going to start focusing on how much oomph it has. You know, its momentum. I can't stress this enough. This is the single most important shift in this entire explainer. And when we cross that bridge, where do we end up? We arrive at our destination, the world of H. This is the Hamiltonian. Welcome to our new and incredibly powerful perspective. So this Hamiltonian, this H, it gives us a completely fresh description of the exact same physical system. And here's why it's so useful. A lot of the time, H just is the total energy of the system. We're talking kinetic energy plus potential energy. And let's be honest, total energy is a much more intuitive thing to think about, right? And right here, you can see the change in action. Look, H isn't a function of position and velocity anymore. It's a function of position Q and this new player on the scene, P. So here's our new toolkit. We still have Q for position, that part hasn't changed, but Q dot, velocity, it's gone. And in its place, we have P, which stands for momentum. Now you might be asking, why is this better? Why do all this work? Well, think about a planet spinning in space. Its velocity to any given point on its surface is constantly changing direction, right? It's a mess. But its angular momentum, that total spinningness, that can stay almost perfectly constant for like billions of years. Momentum often shows us a deeper, more fundamental truth about a system that velocity just hides. We've basically traded a fickle variable for something much more solid. Okay, let's just put it all side by side so it's crystal clear. The Lagrangian world, it's all about position and velocity. The Hamiltonian world, it's about position and momentum. That's the trade. It's the exact same physics, the same universe, we're just looking at it through a different and way more powerful lens. Okay, so we know where we're starting, the world of L. And we know where we're going, the world of H. But how do we actually do it? How do we build that bridge between them? Well, the formula itself is our instruction manual. Yeah, this thing right here, I know. It looks a little intimidating with all those symbols, but I promise you, it's really just a simple recipe with a few steps. It tells us exactly how to take our old Lagrangian, L, and transform it into our shiny new Hamiltonian, H. Let's just walk through it step by step. So check it out. It's basically a 4-step process. Step 1, you take the momentum, P, and you multiply it by the velocity, Q dot. Step 2, see that big E-looking symbol? That's sigma, and it just means add them all up. So you just sum up all those values you just calculated. Step 3, you take that grand total and you subtract the entire original Lagrangian, L. And boom, step 4, what you're left with, that's your Hamiltonian. That's the whole recipe. That's how you build the bridge. Okay, I know what you might be thinking right about now. All right, that's a neat math trick, but so what? Why on earth would physicists go through all this trouble just to swap a few variables? And that is a totally fair question, but the answer is this change in perspective isn't just neat. It's not just a party trick. It is absolutely essential to modern physics. I'm not kidding. This Hamiltonian way of thinking, it's the bedrock of so much of what we know today. It is the absolute non-negotiable foundation of quantum mechanics, a field where energy and momentum are literally everything. You want to understand chaos theory and find the hidden patterns in something as complex as the weather. You need the Hamiltonian. You want to plot the trajectory of a spacecraft going to Mars with mind-boggling precision? You guessed it. You're using Hamiltonian mechanics. This isn't just some dusty academic exercise. This one little change of perspective is what unlocked entire fields of science. It's like a genuine superpower for physicists. And that really brings us to the big idea here. This whole journey we just took from L to H, it shows us something so incredibly important. Sometimes the biggest breakthroughs in science don't come from a new experiment or new data. They come from simply finding a new way to look at the problem, a new perspective. And that just makes you wonder, doesn't it? What other huge secrets of the universe are just sitting there, right in front of us? Waiting, just waiting for someone to come along and find the right way to look at them.